This video is about ideas presented by these brilliant scientists, pictured here at a convention in 1927. You'll notice they're all men, except for Madame Curie, who is right there. All of these people had major parts to play in a revolution in science. This one's Albert Einstein. This one here is Erwin Schrödinger. That one right there is Niels Bohr. That one's Max Born. That one right there is Heisenberg. This one is Pauli. All of these people, every single one of them, has a equation named after them, a constant, a principle. All of these people were major players in the most brilliant revolution in science ever. And it was all about this idea of where are electrons around a nucleus. When last we met, we had talked about the nucleus and this idea that there were certain orbits that electrons could be in. Electron could be here, around, rotating around the nucleus in this path. An electron could be here, rotating around the nucleus in this path. But it couldn't ever be in between them. It can jump from one to the other, but it can't be in between. An idea that had no theoretical underpinnings. The only reason they said it, remember, was to explain the absorption spectra, the emission spectra. So this got people thinking. Mostly, as I say, these people. And they're the ones that started these theoretical underpinnings. And what we ended up with was an entire field of science, and a very important field of science, called quantum mechanics. Quantum mechanics. Quantum mechanics is the basis for a lot of our advances in the world today. Our technology advances, computers, and so forth, are all about quantum mechanics in ways that I can't even begin to tell you in this introductory video. Though I can recommend some books you read. I warn you now, quantum mechanics is challenging because it's very counterintuitive. That's the problem with quantum mechanics. Things behave, particles behave in quantum mechanics the way we are not used to things behaving in the real world. Mostly because they're so small. And we are, in fact, only going to touch on the very surface of quantum mechanics. It's a whole course in and of itself. So the purpose of this video is to talk about quantum numbers and how quantum numbers tell us where electrons are, as much as possible to know, around a nucleus. Quantum numbers are essentially an algorithm, a list of rules. If you follow the rules, you always find the right answer. It's like a computer program. It's a set of rules. Now, there are 4 quantum numbers. There are 4 quantum numbers. Pauli was one of the people in the picture, has postulated the Pauli exclusion principle. The Pauli exclusion principle says no 2 electrons on the same atom can have the same set of 4 quantum numbers. Okay? Which means that the 4 quantum numbers for every electron on an atom is unique. Otherwise, the system wouldn't work very well. We have to have 4 different numbers for every electron on the atom. And that's what Pauli's exclusion principle says. And we will get into a little later some more of those consequences of that. So, let me define these 4 numbers for you. Brace yourself. The first number is called the principal quantum number, and its symbol is a lowercase n. N can be equal to 1, can be equal to 2, can be equal to 3, dot, 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 dot out as far along as you need it. So it starts at 1. It moves up by integers as long as you need it to keep going up. That's the rule for this principal quantum number n. As we go along, I'm going to try to tell you a physical meaning for these quantum numbers. It gets very hairy very quickly, but I will try. If we think about this picture of the atom with its nucleus and its rings, n essentially tells you what ring you are on. So if n equals 1, you're at this first ring closest to the nucleus. If n equals 2, you're on the second ring. If n equals 3, n equals 4, n equals 5, etc., etc. So essentially, the higher the number n, the higher the value of the principal quantum number, the farther away the electron is from the nucleus. You can picture it as a ladder. N is each rung of the ladder. And the higher n is, the higher up you are away from the ground. That is the meaning of n. Now, if you think, again, about being on this ladder, it takes more and more energy to climb these rungs. So, we always start with the lowest n possible. The higher the n, the higher the energy of the electron. And everything always wants to be lowest energy. So we always work to keep the lowest energy, and the higher the n, the higher the energy. Okay? Okay. Now, all the other quantum numbers have a value that depends on what n is. The second quantum number is called the angular quantum number, and it's a lowercase l. Okay? It's a lowercase l. Often looks like a 1 because you're typing it, but it's really a lowercase l. L starts at 0 and again goes up by integers, but it has a stopping point. Unlike n, whose stopping point is technically infinity, L has a stopping point of n minus 1. So you only know what L is in relation to n. If n is 1, the only thing L can be is 0, because 1 minus 1 is 0. If n equals 2, L has two values, 0 and 1, because it always starts at 0 and goes up to 1 less than n. And 2 minus 1 is 1. So 0 and 1. So remember, L doesn't have just one value. L isn't just n minus 1. It is, in fact, starts at 0 and goes up to n minus 1. So if L is 3, 3 minus 1 is 2, and the values for L are 0, 1, and 2. Okay, so there's more than one possibility of L, depending on what n is. Okay, physical reality for L. Here's where our nice mental picture begins to break down. Remember that I said n were rings on a ladder. Well, the minute we get to L, this pretty picture of rings goes away. L represents shapes. Areas of probability, this is all about math, areas of probability where the electron is. Okay, once again, probability. Quantum is all about probabilisticness. It's not 100% certain that the area that we lay out is where the electron is. It's something like 98% certain. But it's where the electron probably is. But these areas of probability do not have a physical existence. That is, if you were somehow to shrink yourself down, like Miss Frizzle and the Magic School Bus, and stand on a nucleus, you would not see like little areas of blue or something that says, this is the L equals 0 area probability. It isn't real. It's a mathematical construct to help us decide where on Earth this electron is. Okay, now knowing that, let me draw some drawings for you. If L equals 0, the area of probability where the electron is a sphere. A sphere centered at the origin, where you can think about this is where the nucleus is, at the origin, where X, Y, and Z meet. Remember, it's not really X, Y, it's really X, Y, and Z. It's a three-dimensional world. But a three-dimensional sphere, somewhere in there with the center as the nucleus, is where the electron is, if L equals 0. Now, this actually has a name. It's called an S orbital, for reasons that are lost in the history of time. S doesn't actually have a meaning today. It used to, but it doesn't anymore. But it's still called the S orbital. Okay, now remember what we said about S, or about L. L depends on N. So no matter what N is, there is always an L equals 0. N equals 1, there's an L equals 0. N equals 2, there's an L equals 0 and an L equals 1. N equals 3, there's an L equals 0 and an L equals 1 and L equals 2. There is always an L equals 0, no matter what N is. So every atom has at least an S orbital. So what's the difference between an N equals 1, L equals 0, an N equals 2, an L equals 0, an N equals 3, an L equals 0? The difference is essentially the size of that sphere. Here's a picture that shows that. There's your N equals 1, L equals 0 sphere. There's your L equals 0 when N equals 2 sphere. Here is your L equals 0 when N equals 3 sphere. We're essentially getting bigger and bigger. So far, so good? Okay. Now, let's say L equals 1. If L equals 1, it's called a P. Again, for reasons we won't go into, because it really is kind of meaningless these days. L equals 1 is called a P orbital. A P orbital is like a dumbbell shape. It's like one of those long, thin balloons, but pinched in the middle. Because remember, this is three-dimensional. This guy right here, this pinch in the middle, is called a node. A node is a place where the electron cannot be, absolutely. In the case of a P orbital, the node is where the nucleus is. I will get more into a P orbital and what it looks like in a moment. I told you these are getting complicated. Let's leave the P orbital looking like this for the moment. Though I'll have more to say. If L equals 2, I have what's called a D orbital. For the most part, a D orbital is like a clover leaf. I'll show you real pictures, not based on my art, a little bit later. But a picture like two of those long balloons crossed in the center with a node. Again, there's that node in the center where the nucleus is. That's what a D orbital looks like. There's one more that we actually encounter in the real world. Though theoretically, of course, this could go on forever, but eventually we run out of electrons in known elements. So as far as we need, it's L equals 3. And that's something called an F orbital that I am not even remotely going to try to draw for you. In almost any chemistry textbook stops drawing at the D. It's essentially a more complicated cloverleaf. You don't need to know. Alright, so that takes care of two of the quantum numbers. We've got N, we've got L. The third quantum number is called the magnetic quantum number. that is represented by a lowercase m subscript L. Okay, a lowercase m subscript L. M sub L, that's pronounced. M sub L. You can't just say M. It has to be M sub L. M for magnetic. Magnetic quantum number. Now, M sub L depends on L, as you can imagine from that subscript. That L is a label, by the way. It's not like you substitute L in there. It's simply a label. It's simply saying the M that depends on L. The rule for M sub L is that it begins with negative L, goes up by integers to 0, and up again until it stops at L. So if L is 0, M sub L can only be 0. If L is 0, M sub L can only be 0. If L is 1, M sub L has 3 values. Negative 1, 0, and 1. If L equals 2, M sub L has 5 values. Negative 2, negative 1, 0, 1, and 2. It always starts at negative L, goes up by integers until it gets to positive L. Now, physical reality for M sub L. M sub L talks about the orientation of the orbital in space. Remember, we're talking about a three-dimensional object here, this orbital. The number of M sub L values talks about how many ways I can orient the orbital in space. So M sub L has only one value. For L equals 0, M sub L is only 0. Because L is a sphere. There really is no other way to rotate a sphere to make it look any different. So there is only one L equals 0. There is only one s orbital for each n. But L equals 1 has 3 different M sub L values. Negative 1, 0, and 1. Which means, in fact, there are 3 orientations in space for L equals 1, for the p orbital. One along the x-axis, one along the y-axis, and one along the z-axis. Here's a picture. Okay, there are 3 p orbitals, one along the x-axis, one along the y-axis, and one along the z-axis. Remember, this x is really coming out of the screen toward you for each value of n. Remember, I can't have a 1p because there isn't any such thing as an L equaling 1 if n equals 1. But I can have an n equals 2, L equals 1. So that's the 2p orbital. But I can also have a 3p and a 4p and a 5p. So these do repeat themselves. Now D has 5 values. So there are, in fact, 5 different d orbitals when it exists. When I get high enough up in n to have a d, each time I do, there are 5 different possible d's. Here's what they look like. This is called the dyz, this is called the dxz, this is the dxy, this is the dx squared y squared, and this is the dz squared. Those are just labels. Don't worry about what they mean. It really just has to do with its orientation in space. Now, f orbitals, negative 3, negative 2, negative 1, 0, 1, 2, and 3. There they are. 1, 2, 3, 4, 5, 6, 7. There are 7 of those. Here's what they look like, though you may regret asking. That's what they look like. I will never, ever ask you to reproduce an f orbital. Okay, now, All of that's only 3 quantum numbers. There's actually one more. Don't worry. This one's actually much, much easier. You'll love this one. The last quantum number is called the spin quantum number. This is again that lowercase m, this time sub s. Hence why they had to have subscripts to them to distinguish them. The magnetic quantum number is m sub l. The spin quantum number is m sub s. M sub s has only 2 possible values. It's either 1/2 or it's negative 1/2. That's it. Only 2 values. 1/2, negative 1/2. Essentially, it means, well, you can think of it as meaning the electron's rotating clockwise or it's rotating counterclockwise. That's not really what it means, but it's a pretty good approximation of what it means. So it's still in that same orbital, it's still in that same area of space, still in that same area of probability, but it's either spinning in one direction or the other. Hence why it's called the spin quantum number. Okay? Okay. Now, let's apply these rules to particular elements. Let's start with hydrogen. There is in hydrogen 1 electron, right? So we need 1 set of 4 quantum numbers for this 1 electron in hydrogen. So here's my rules. First n, I want to start with the lowest n I can possibly start with. That's n equals 1. Because again, it's all about energy, and I want the lowest energy. I want the nearest thing to the nucleus. So n equals 1. So my first quantum number is 1. Now once I've defined n, I can define L. L starts at 0 and goes up to n minus 1. Well, 1 minus 1 is 0, so the only possible value for L is 0. So that's 1, 0. Magnetic quantum number, m sub L, starts at negative L, goes up through 0, goes to positive L. So again, if L equals 0, there's only 1 possible value of m sub L, and that's 0. So 1, 0, 0. The magnetic, or the spin quantum number rather, the spin quantum number has only 2 values, 1/2 or negative 1/2. By convention, that is simply because we all agree this is what we're going to do, the first time I use m sub s, I use the positive. So that's positive 1/2. So the 4 quantum numbers that describe the 1 electron in hydrogen are 1, 0, 0, 1/2. I can call that a 1s electron because this is 1. This L equals 0 is s. Okay, it's a 1s electron. And one way to draw that is to draw a dash to represent the 1s orbital. I'm going to label it 1s. There is only 1 dash. That's this idea that m sub L has only 1 value. And this guy, positive 1/2, I'm going to represent as an arrow pointing up. So the shorthand to 1, 0, 0, 1/2 is this pretty picture here, 1s with an arrow pointed up. Now, helium of course has 2 electrons. So we need 2 sets of 4 quantum numbers. The first one is going to be exactly the same because we are going to follow the exact same procedure to get it. 1, 0, 0, 1/2. Second electron, we are going to say 1 again, 0, 0, because once n is 1, these 2 can only be zeros. But remember Pauli exclusion principle. Pauli exclusion principle says I cannot have the same set of 4 quantum numbers on the same atom. So I can't say positive 1/2 this time. I have to say negative 1/2. So those are the 4 quantum numbers for the 2 electrons on helium. And when I draw my little dash here and call it 1s, I have an arrow pointing up and an arrow pointing down. The arrow pointing up is this guy with the positive 1/2, and the arrow pointing down is this guy with the negative 1/2. Those are the 2 electrons in helium. In reality, of course, it's this area of probability that's spherically shaped around the nucleus, and somewhere in there are these 2 electrons. But this is the shorthand. Now let's go with lithium. 3 electrons in lithium. The first 2 are these 2. We are always going to be repeating ourselves. 1, 0, 0, 1/2. 1, 0, 0, negative 1/2. That's the first 2 electrons. Now the third electron. I am out of possibilities for n equals 1. There is no other set of 4 quantum numbers I can get, starting with n equals 1, that follow all of my rules. That being true, I now have to move on to n equals 2. n equals 2. L can be 0 or 1. Again, I want the lowest value I can, so L equals 0 first. Before I go through the L equals 1s, I have to go through the L equals 0s. That's going to be 0, 0, positive 1/2 again. So in terms of this, I have run out of space on my 1s dash. I now need a 2s dash, right? Because n equals 2 and L equals 0, so that's 2s. I have a 2s dash, and this 2s dash has an electron with a positive 1/2, so that's an arrow pointing up. Again, by convention, I just do that. I just say we're always going to start with the arrow pointed up. So I bet you can figure out the next one. Beryllium, 4 electrons. I'm not going to keep repeating myself. The first 3 are these that I already wrote. The last one, the new one in beryllium, is 2, 0, 0, negative 1/2. So that's 1s with my arrow pointing up and my arrow pointing down, and 2s with my arrow pointing up and my arrow pointing down. Okay, 4 of them. These 3 from lithium and this new one. Now boron. There are 5 electrons in boron. These guys, these 4, and now my new one. I have now run out of 2, 0 possibilities. That's all there is for 2, 0. I now have to move on to 2, 1. Remember, I'm not out of 2 yet. I still have possibilities for n equals 2. But now I have to move on from n equals 2, L equals 0, to n equals 2, L equals 1. So this is 2, 1. Now, about m sub L. Now I'm reached the point where I have more than one value for m sub L. So again, by convention, we're going to start with the lowest, go through all those possibilities before I move on. You'll actually find books that will start here, but we are going to start here. Okay, so if L equals 1, negative L is negative 1. So 2, 1, negative 1, and again, by convention, positive 1/2. So now I've got the 1s orbital, the 2s orbital, but now I'm at a 2p orbital. Remember, there are 3 possible values for m sub L. So even though I'm not going to put an electron in all 3 of them, I have to draw 3 dashes for the 2p, representing the 3 different values of m sub L. This is the negative 1 m sub L, this is the 0 m sub L, this is the positive 1 m sub L. And again, it's the arrow pointing up. So these are my 5 electrons in boron. Alright, let's skip ahead a little. can figure out carbon. Let's go to nitrogen. Nitrogen. Okay. 7 of them. So we've got the usual 1, 0, 0, 1 half. That was all the 5 that I did before. Now it's 2, 1, 0, 1 half, and 2, 1, 1, 1 half. Again, by convention, I always do the positive 1 halves first. So if I draw this in my orbital notation, which is what this part is called, 1s, 2s, 2p, all 3 of these are the 2p. I always draw this so each one of these has 1 pointed up before I start pairing them. Okay, obviously in the next one I'm going to have to start pairing them. The next one, on the next atom, it's going to put the 1 here. But for now, I have 1 facing up each. That leads me to another rule. Okay, we had Pauli exclusion principle. Now we have Hund's rule. Hund's rule. When I was a little girl, my chemistry teacher called it the bus rule. And I always thought that was a very good way to remember it. The bus rule is, whenever I get on a bus, I sit by myself, as long as there's an empty seat. I only sit with somebody if I'm forced to sit with somebody. And that's what Hund's rule says. It says electrons, because again, it's all about being in the lowest energy. Always lowest energy. If, let's write it this way, if the orbitals have the same energy, i.e., they have the same N and L, okay, then the electrons will enter an empty orbital before they fill one, before they pair up. They only pair up when they're forced to. Okay? It always looks like this. It's never up, down, up. It's always up, up, up until it's forced to pair. Okay? Okay. Let's move on to neon, which is as far as we're going to go. Neon is 10. 10 electrons. Here they all are. Ready? Brace yourself. 1, 0, 0, 1 half. 1, 0, 0, negative 1 half. 2, 0, 0, 1 half. 2, 0, 0, negative 1 half. 2, 1, negative 1, 1 half. 2, 1, 0, 1 half. 2, 1, 1, 1 half. Those are all the ones I already did. Now the new ones. 2, 1, negative 1, negative 1 half. 2, 1, 0, negative 1 half. 2, 1, 1, negative 1 half. Okay? So this is 1s, 2s, 2p. And remember, they're filling into the 2p. 1, 2, 3, 4, 5, 6. Okay, there are 10 electrons here. I am actually done with n equals 2. There is no other possibility for n equals 2. The next electron, I am going to have to go into n equals 3. Well, let's take a look at this. How many do I have here in n equals 1? 2. How many do I have here in n equals 2? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 possibilities. 8 possibilities for n equals 2. This should sound really familiar to you. Last year in biology, what did your teacher tell you? She told you there were 2 electrons on the first orbit and 8 electrons on the second. Remember going back to this picture? There's my nucleus, there are my rings. There are 2 electrons here. And 8 electrons here. 2, 8. That's why she told you that. 2, 8. And if you think about what a periodic table looks like, this first row here has in fact 2 electrons on it for n equals 1. This second row here has 1, 2, 3, 4, 5, 6, 7, 8 electrons on that for n equals 2. The periodic table is laid out totally according to electron configuration. Where are the electrons? These numbers on the side correspond to n value, and that is the perfect place to stop.